Hello, welcome to the pre-recorded presentation of online facility allocation with linear delay. My name is Martin Böhm, and this is joint work with Marcin Binkowski, myself, Jaroslav Birka, and Jan Marcinkowski, all in University of Wrocław in Poland. So let me move to a more comfortable position. There I am, and let's go. So online, you probably know facility allocation. It's a very famous problem, but let's sort of refresh it with a funny example. So imagine we are a startup company with a brand new invention. So we can pay one of the several facilities, so like this one on the right. We can pay one of the several facilities, so factories in the world, throughout the world, to do sort of a short test run or production run of our tool. And then this is a problem with clients as well. So as we sort of advertise our tool, clients appear all over the world, so in various places and at various times, of course, as they see our, our ads and our newsletters, and so and they want our tool, right? So our what's the online component in this problem? Well, these clients appear at an unknown time, and we only learn about them once this sort of time appears, right? So only once they become active, we sort of learn about them. And they are infinitely patient, so they can wait a bit for the production of their tool that they want now, but the patience equals client-side delay that we want to sort of minimize overall, right? So you can see that sort of we think of them as circles. So let's see an example that's more mathematical. So we can see that time sort of flows in this picture, going up. And then we see the metric space that we're sort of working on. And you can see that there's like copies corresponding to slices of time of this metric space. In this metric space, you can already see our smiley faces, our circles corresponding to clients somewhere in the metric space. And you can see gray squares, which correspond to the positions of potential facilities, where we can open a facility, meaning paying the facility for a short production run of our tool, right? And you can see at time t1, there's 2 clients, but we decided not to open anything, not to start any run. So they're waiting until time t2, where a green client arrives, and also nothing is happening so far. So they wait until time t3, and now there's a 4th client arriving, and those that have been there already paid some sort of delay, right? And the delay is linear with time, so it's literally, for example, for this one, it's t3 minus t1, right? So all delays are linear with time. And it's also worth noting that we can think of facilities to have different opening costs. This is not a problem. Right. So you can see that the slices have shifted. Now we have T2, T3, T4. So at time T3, we had the 4 clients here, and we decided that maybe it's time to do a production run. So we have opened the facility, paying its opening cost, and we have connected several clients to this facility, meaning we have sent them the shipment, and we sort of don't care about the number of tools that we're creating now. It's the cost that we're paying now in facility location is opening cost plus connection costs. Right? So we've connected these 3, and this one is still waiting for its tool. So this goes just up, right? And you can also notice, which is important, that the facility is only open at a particular time for a really short time. So in principle, it's not open permanently. It's not like we're buying the factory, right? It's only like we're only leasing it for a brief moment, or tasking them with producing our tool. So for example, this ping client would like to also connect here because it's quite close to them, but unfortunately the facility is no longer open, right? So they could open it, we could open it again and connect them to here, but this would mean a new opening cost here, and of course the connection cost, right? So this is the model with one-sided delay. This has been studied in the past, and we have a little extension that actually allows us to do some nice things. So what's this extension? So you should think about a model, we call it two-sided delays, and you should think about crowdfunding models, right? So if you've ever been purchasing something on these crowdfunding sites, you know that there are usually discounted like early adopter tiers. So you can buy something like in the one-sided delay model that you only wait and then you get it. and you pay a reasonable price. But sometimes we also want to allow late adopters to sort of pay for our production cost and sort of make it smoother. So we also allow late adopters, but the tier is maybe a little bit more expensive, right? So we sort of have this model. We have this price increase in this model as well. In this two-sided model, we allow late adopters to connect to the facility at time t prime later than we did the run, but they have to pay a facility side delay cost of t prime minus t. Right? Let's see it on the picture. So we had the pink and the green client that were not connected at time t4, but we can now connect them in this two-sided model. We can connect them to this original run at time t3, so essentially to the same facility without opening cost, but they need to pay this extra delay, facility side delay of t4 minus t3, right? And you can see that both of them need to pay it, right? So it's not like one cost only for the facility, but everybody who connects this way needs to pay it. And also you can see that the pink client who was not in at time t3 even available or known can also connect sort of to time t3, right? So it's not only the green client who has waited all this time, but it's also this pink client who just appears later. So this is all allowed. You can, if you're a bit imaginative, you can kind of imagine a futuristic world, nonsensical world, where time travel is not only possible, but it's also at linear cost, right? So if it's really linear cost of time travel, then you can imagine so the pink client to travel back in time to the production run at time t3 and getting the tool only at this extra cost of t4 minus t3. But that's of course not how we want to think about it in the real world, but it's just a fun thing, fun way to remember it, right? So this is this facility side delay cost through which we can connect to a facility that's been opened in the past. And of course, we have the possibility of reopening it again and not paying this cost. That's up to the algorithms, right? So why is this two-sided delay model interesting? Well, it's sort of interesting because it allows, because we know a constant competitive algorithm for it. So our results, first result is that there exists a 3.869 competitive deterministic algorithm for this model, online facility location with two-sided delay, where everything, all delays are actually linear. And in fact, we can also show an extension that applies to one-sided delays. So there exists an O log n over log n competitive deterministic algorithm for the one-sided delays, where we of course use this two-sided delay model. So we sort of emulate the two-sided model in the one-sided model. And it's nice. I mean, this competitive bound is not a big improvement. The previous bound was log n, but it's still better than what was known before. So it's kind of nice that it actually applies. And of course, we would like to see this drop further. There are no theoretical reasons currently for why this couldn't be lower, but that's maybe up to you. So let's see first the two-sided model and why does a constant competitive algorithm actually exist. So let's talk about the algorithm. This algorithm actually comes from the world of approximation algorithms, where there's been several strong algorithms for facility location, and this is sort of an adaptation of one of them. So we have our algorithm is parameterized with a constant gamma, that's bigger than 1, and we think of every client as sort of, you know, this classical ball growing idea that they grow their budget of gamma times how long they have been present in the system, right? So t minus tj. And each active client, so clients that have not been connected yet, they offer, of course, they need to pay for the connection cost with their budget. But once the connection cost is paid, they would like to contribute towards opening a facility. So the leftover is budget minus distance, and this is going towards sort of an offer towards opening a facility, right? So what does our algorithm do? Well, if a new client arrives, we start growing the budget. And if for any location, the sum of contributions reaches the opening cost of this location, we want to open. So we select clients that can afford paying, that have a budget at least for the distance, we open the facility because their contributions of the richer clients can afford it. And then we connect every client that can afford the distance to it, right? So this deactivates them and we don't grow their budgets anymore, of course. And there's also the possibility of our two-sided delay. So we could connect sort of to a facility open at the previous time, right? So if for a facility that has already been open at time tau, some earlier time, and for an active client, this client can now pay the facility side delay cost with its growing budget. We connect this client to the facility at time tau, and he pays the connection cost as well as the facility side delay, right? And once any client is connected this way, they become inactive and the ball is not growing anymore, right? So the algorithms, so the ball growing kind of algorithm. And in fact, if you know algorithms for approximating facility location, sort of without any time notion, then you know this is a modification of the classical sort of JMS algorithm, right? And our analysis, I mean, now if you know the JMS analysis really well, maybe you can already give an analysis of this one, but we show a slightly different one. So let's sort of dig a little bit deeper into what the analysis is going to be, right? But the start is the same. We sort of want to investigate some linear programs that are called factory linear programs and whose bounds actually describe the competitive ratio of the algorithm. Right. So we have the LP here. You can see that there's a lot of variables. Let's actually try to understand them before we read the LP. So the LP is written so that it focuses on one facility F, and we can imagine this facility is open at time 0. So by opt, right? So all the clients, of course, can choose different facilities for the adversary, but we only consider the clients at S that opt connects to this F, right? So this is the star where we play. And we already have the parameter gamma, that's the multiplier. And we also have heard about the opening cost, and that's represented by OpenF. So we have clients that actually need to arrive at some points. So when a client J arrives, this is the arrival time, this is where it appeared. And we also have service time, meaning they grow their budgets, and at some point ALK actually connects them somewhere, right? So this is the service time when ALK decides to connect them somehow. And of course, there's also the distance, right? But we don't have distance between 2 points. At this point, we only focus on facility F. So we have DJ, distance from F to client J. So with these variables in mind, we can try to read through the LP and see what the constraint and the equation say. So first, the optimization. So we maximize, and we would probably like to maximize ALK divided by opt. So let's see if that's the case. Well, we know that gamma, so what's SI minus AI? Well, that's the time how long the connectivity budget actually grew, because at time SI, we stop the budget and we probably connect. But the budget is, of course, gamma times, right? So gamma times SI minus AI, that's the connectivity budget of client I, and we sum, so we sum over all the clients. But what's this one? Well, the cost of ALK is not only the connectivity budget. In the worst case, of course, each client needs to pay the full connectivity budget, but also we have the client-side delay, right? So the client-side delay is not represented in the budget. It has to be paid sort of separately, and that's why there is one, right? So this is the client-side delay, of course, can be computed by the time from the time where it arrived to the time where it was serviced, right? Connected somewhere. So this is why this is 1 plus gamma. This is the cost of ALK. And what's the cost of opt? Well, we know by assumption that opt opens F, and then we sum up the costs of connecting to the star of clients at S. So of course, all the distances, they're summed up, but of course, opt can also have some delay cost, either client-side delay, or of course, if AI is positive, this means that it's essentially facility-side delay. So this is why there's absolute value, right? So you can see that there's a ratio and there's some absolute values, but all of these things can be linearized quite easily. You shouldn't really worry. So this is indeed the worst situation, ALK over opt. So in principle, this means the maximum value, or a value that upper bounds all the LPs, is a competitive factor. So what are the constraints? Well, this is just a reordering constraint. We want the service time, so the times when client I is connected, to be less than when I plus 1, right? So in principle, we just reorder the client so that this is true, that the I plus first client is connected later than the ith client. Now the fourth constraint is a bit interesting. So what can we see here? Well, we can see that it's for all L less than K. So something is measured from L to K minus 1. So L is some client, but we can also think about the service time of this client as L, right? Something is measured just before time as L, when this L and all the other clients are in principle in the system, right? So L plus 1 and so on. So what should we measure? Well, we should measure the amount of budget that they have not only for connection, but for opening facilities, right? So this is captured by this max. If they don't have, and in fact, we want to measure it at the facility for facility F, right? So if they have no budget for opening a facility F, then this value would be 0. Otherwise, it's gamma times SL minus AI minus the distance, right? Minus the budget for connecting. And if this, and of course, in principle, these clients, so from the Lth to the K minus first client, could decide to open the facility F. But since they sort of didn't, or if they did, then this inequality would be actually the opposite way, right? So the fact that they didn't means that the sum of their budgets for opening is at most the total opening cost of F, right? And then there's this constraint that's essentially, you can see di plus dj, so you expect some kind of a triangle inequality, and it is indeed a triangle inequality, but it's a little bit strange. So we're going to have a special slide just for this. It's actually not that difficult to say. You have client, so again, in this picture, you have time going up. You have client I, and he's going to get serviced, so he's going to get connected later. And you have client J, and his service time is earlier, so by assumption. And what do we want to say? We want to say, well, the client I, since J is connected earlier, there's already this open facility here, the black square, in the past. In principle, client I could connect to this, right? Only pay the whole budget to the connecting cost and be done. So there must be an equality sort of that maintains that he can do this, or he would have done this if this is cheap enough. So what does it mean cheap enough? Well, we just look at his whole connectivity budget and we say that this must be at most, well, this distance, this is di plus dj, and then this distance, which is because of linearity of time, it's si minus sj. So it's this part, right? And then this whole part can be upper bounded by the budget of j at time sj. When his budget froze, so this is gamma times sj minus aj, right? So it's just a 3-part triangle inequality that looks a bit wonky, but it's easy to understand, right? You should check the slide again if this was a bit too fast, but it's really nothing complicated. So our proof approach is that we know that LP1 is a factor being LP, right? And in principle, if we find the largest possible value of zk gamma guaranteed over all choices of k and gamma, this would be the for a smart choice of gamma and for all choices of k, this equals the competitive ratio of the algorithm. However, you cannot really find this that easily because zk gamma is increasing for larger values of k, meaning the more clients in this star there are, the worse the competitive ratio is, maybe only by a small amount, but still that means that solving one of these LPs is not enough. Right? You would need to have a smart argument like in the original JMS approach, like a technical analytical argument showing some upper bound for all k's, and this would be enough, and you could do this. But and we also do that, but we do it with another LP, and it's kind of it's nice because then we can only solve one LP and have a bound on all zk gammas. So this is the LP2, and the nice thing about it is if you implemented the first LP, you have this one as well. You only change one thing, meaning when you're checking the budgets, whether they're enough to opening at capacity F, you do this sum for all at time SL, but you sort of, the client L itself, who was part of this sum, you sort of leave there, right? So the remaining ones, they have to have this budget less to open F, but maybe this one could rise, maybe the Lth one could raise it over, but for this LP2, we allow it. And what's nice is already this small change makes it so that the optimal value of this LP2, yk gamma, is bigger than yk times m gamma for k times m. So for a bigger value of this parameter k, right? For k prime bigger, this means that these values are actually non as this grows, they're actually non increasing, right? So this means that a bound for a fixed k is bounding all of the k times m or k primes in the future, and in particular you can also show, it's not very surprising, that this LP is upper bounding all zk, so all the previous LPs, right? Because this is just a looser version. Yeah. So we would need to prove this proposition, and we're a little bit short on time, but I want to show you that, I mean, there's a little bit of technique needed, but it's literally in the paper and in this slide, that's all you need. You're essentially checking for inequalities. You create sort of you want to show that for the coarser LP is feasible if the smoother LP is feasible, so you somehow sum up the smoother LP with more variables into some chunks, and you show these equalities for the chunks, essentially just using Jensen's inequality to jump out one sum, and you're done. It's really easy. I'm rushing a little bit, but it's really easy, and easier than the original JMS. And what this gives you now is that this LP yk gamma, as I've said, you can just solve one of them for as large k as you can, and for a smart choice of gamma. And this gives you an upper bound for the same gamma for all choices of the LP1, right? So this indeed gives you a competitive ratio. And the only thing you want is that the k is big enough such that the gap between the best possible value of y and, of course, the best possible value of z are not that far apart. And we claim that for k equals 1500, there exists a 3.869, the value is 3.869, so there exists a 3.869 competitive deterministic algorithm for the facility location with two-sided delay, where all waiting costs are linear, right? Because the one LP that we solve, essentially, I mean, we solve a lot, but just to find the right one, a right choice of gamma, so this upper bounds all the zk's, right? Even for the case where zk prime is bigger than 1500. And we've also numerically explored values for zk to see, okay, so how close to this number they are, because this essentially a number that you get there is a lower bound of your technique, essentially, right? So it tells you that this technique cannot be better. You can maybe shave this a little bit, but not much. And what we show is empirically, not proof, is that essentially the technique is definitely not better. I mean, the algorithm with the analysis is definitely not better with 3.861 competitive, right? So the difference is really, really small. And as I've said, we can actually use this two-sided delay result to show a one-sided delay result, which is sort of the more important part. We can shave a multiplicative factor of log n, and we claim that there exists an O log n over log n competitive deterministic algorithm for the online facility location with one-sided delays with everything linear. So what's the idea? Well, you emulate the two-sided delay algorithm that's constant competitive, and you open whenever it opens the facility. And of course, but sometimes it doesn't open. It does this facility delay cost. It pays it. So you sort of accumulate the budget for this delay cost, and once this budget grows enough, you reopen the facility and you connect the people that were originally just connected with the delay, right? And you sort of scale this appropriately, and you shave off this log n. It's neat. So for research directions, you could definitely improve the constant 3.869 with a different algorithm probably, or a different analysis, but you could. More interestingly, you could think about whether the world of approximating facility location, so where we borrowed from, also offers other tools, or this tool, where you can shave the competitive ratio for one-sided delay below the O log n that we could. Could you do O log n? Could you constant? And in fact, there's many open problems around facility location in the online world, in the approximation world over time. So I invite you to look at the two references that I've presented here, one both recent, one from Fox 2020, one from IPCO 2020, and you're going to see some open problems in there as well. So thank you for your attention, and enjoy the rest of APPROX.